My name is Dushyanth Narayanan. I work for Microsoft Research, and I'm going to talk about how the cloud is influencing the research we do in the systems area. Okay. So a little bit about Microsoft Research. We're a part of Microsoft, right? And within Microsoft, we have sort of multiple goals to advance the state of the art in computer science, but sometimes in other fields as well, and then to take those advances and use them to improve the products and services that Microsoft offers its customers. And more ambitiously, to disrupt existing technologies and create entirely new businesses. So this is what we see ourselves as a sort of longer term, 5 years and out, value creation engine for Microsoft. Okay. So Microsoft Research started in 1991. Our first lab was in Redmond, Washington, where the corporate headquarters are. Today we have more than 1,000 researchers and engineers all over the world. Cambridge in the UK is where I spend my time. And at the Cambridge lab specifically, we've sort of broadly think of our research ambitions as falling into 3 very broad and overlapping themes. Right? So the first one is to advance the state of the art in AI and machine learning, and also to apply those techniques to improve people's lives. The second one is to improve, to transform the way people collaborate and communicate online. Right? And the third one, which I will focus on today, is to invent the cloud infrastructure that is needed for these first 2 pillars, and in general is going to support the computational and data demands of Microsoft and its customers in the future. Okay. So when you talk about cloud and you work for Microsoft, there's a very clear path to influence Microsoft and the world, and that's Microsoft Azure. That's the division of Microsoft that deals with our cloud offerings. And to give you an idea of today's scale of Azure, we have data centers in about 50 regions all over the world. Each region has 10 to 12 data centers, and each data center has hundreds of thousands of servers. And this is sort of a snapshot. There's very rapid growth in both the number of data centers and the number of regions that we're putting in almost every month. Okay. So when you're running something at this scale, there are huge numbers of challenges and opportunities. And for a sort of technical research audience, I'm going to talk, and as a technical research person, I'm going to talk about the more sort of researchy end of the challenges, right? And so the scale is obviously a challenge, right? Whatever you do, it needs to potentially be able to run on these massive data centers, across data centers within a region, and in some cases across regions. Right? Cost is hugely important, right? Again, when you're buying hardware at this scale, and you need to be able to sell services on it at a profit to your customers, you cannot spend stupid amounts on hardware. So we have to be very conscious of cost in anything we design. But performance is equally important, right? Low latency for some applications that need it, and high throughput per server for many, many applications, because again, high throughput per server can translate to fewer servers, lower cost. Right? Availability, right? Many of our cloud services need anything from 3 to 6 nines of availability, right? Because our customers build services on top of those, which are eventually exposed as, for example, websites, and when websites go down, people lose money, right? And security, right? Extremely important. We need customers to be able to trust that malicious actors, both internal or external, cannot tamper with or compromise the privacy of the computation and data they run in Microsoft's cloud, right? And this is very crucial, right? We rely on this trust, which means we have to deliver it. From a research point of view, I think cloud also offers some unique opportunities. And one of them is the fact that because of the scale at which we operate, often we're able to go back and do a clean slate design. Right? We're able to rethink the entire stack, hardware and software. And this is a bit different from maybe, say, the mobile phone world, where if you do something, it has to fit into a very large ecosystem of parts, of software, of hardware. In the cloud with a service-based API, most of the time, you can abstract away the details of your hardware and software implementation under that API transparently to users. And that gives you a lot of opportunity to make big changes. And so related to that idea is this idea of hardware-software co-design, which especially at the lab, we've been increasingly pushing in our projects because we find it brings great value to think of the two things together and how best they can provide a given service. So we have a bunch of projects in the systems and networking area at Microsoft Research Cambridge. The project names are in red here. I apologize for the awful colors. I'm not very good at designing slides. I'm going to be talking about some of these projects over the next half an hour or so. But I think something that I'd like you to take away is that not only overall do we span a fair number of areas of expertise for a group of about 30 people, but increasingly our individual projects are very interdisciplinary, right? We bring together people from very diverse areas of expertise, right? Optics people, distributed systems people, security people, etc. And partly that's because of this push we're doing towards sort of clean slate design. So you'll see a few examples in the talk, but if you're going to design something from the bottom up, you need this range of expertise. The other thing you might have noticed is this cloud down there. And at the Cambridge lab in particular, over the last 5 years, we've been building up a substantial amount of expertise in optics. So these are people who understand lasers, who understand diffraction, wavelengths, mostly things that I don't understand in great detail, but I go to them and ask silly questions and try to learn. And this expertise in optics has enabled us to push the boundaries in the areas of storage and networking, two things I'll talk about later, right? And we couldn't have done this without this range of expertise. Okay. So I'm going to start by talking about Farm, which is one of the older projects I'm going to talk about here. I'm a little bit biased because Farm is a project that I started along with some colleagues and have been working on for the last 6 years. And the core observation that Farm starts with is that when we looked at distributed computing platforms, right, we saw that there were good platforms for batch computations at scale, right? Things like MapReduce, which can run on thousands of machines, process huge amounts of data in hours. And there were reasonably good platforms for interactive latency type computations, but which didn't scale out. Right? There was no good general platform for low latency at scale. Right? And so Farm fills this gap. It provides a platform for applications that need low latency at scale, and in addition, we're pushing latency down by 2 to 3 orders of magnitude compared to what other online systems, comparable online systems could do before. So Farm is a platform, and what it does is it makes it easy to build low latency distributed applications by using distributed transactions and replication. Right? Distributed systems are messy. Right? You have many threads running many operations concurrently, which may access the same data on multiple machines, each of which may fail at any time. Right? Farm hides failures, data distribution, and concurrency from the programmer and provides a very simple abstraction of a single giant machine that runs transactions one at a time and never fails. So distributed transactions are not a new idea. We certainly didn't invent them. I think they predate from before I was born. In the past, though, many people believed that distributed transactions would perform poorly. And so they compromised the abstraction in order to get performance. So in Farm, we showed that within the data center, you can have distributed transactions with strong consistency, high availability, and very good performance. To achieve this performance, we exploited some trends we saw in data center hardware. So first, cheap and plentiful DRAM, so we can keep working sets in DRAM for many applications. Second, we can make all this DRAM non-volatile at relatively low cost simply by adding commodity lithium-ion batteries and SSDs to each rack and saving the DRAM to SSD on power failure. And finally, fast RDMA networking to cut the cost of scale-out. But we also found that if you take existing software, scale-out software, and use it unmodified, you don't see the benefits that this hardware promises because there are CPU bottlenecks that were previously hidden under the much slower I/O that these systems were using. So we had to redesign the communication stack and the distributed system protocols, and this is where a lot of the technical work of FARM went into. So to go a bit deeper into that, into what it means to redesign the communication stack, well, to exploit this fast networking hardware, you have to use it right. And this graph is an illustration of what that means. So this is a very simple micro benchmark we ran on a cluster of machines connected by an RDMA Ethernet network. And each of these machines is randomly reading in-memory objects from a different remote machine. Right? And the x-axis is the size of the object you're reading, and the y-axis is the network throughput you get per server. And what we found is that fast RDMA-based messaging is an order of magnitude faster than using TCP on the same hardware, and using these one-sided RDMA reads rather than two-sided RDMA-based messaging gave us another factor of 2. Right? And so how do we exploit that? And so a large part of FARM was about exploiting this observation in order to redesign all our communication to use one-sided RDMA where possible and two-sided RDMA-based messaging for the rest of it, and not use TCP at all. So here's one example of what we redesigned. We run distributed transactions, and distributed transactions need a distributed commit protocol. Right? So if you think about a transaction running on a machine C, the coordinator, with time going from left to right, it might read an object which is stored on a server P1, and then perhaps read another object stored on server P2, and then maybe it wants to write that second object. Right? And because we need to be highly available for fault tolerance, each of these objects is replicated. In this example, that's one primary and one backup copy for each object. So a traditional two-phase commit, what you would find in your database textbooks, when you want to commit this transaction, you would send a prepare message to all the participants of the transaction, right? All the primaries and backups of all the objects you read or wrote. And if the prepare succeeded, you would send a commit message. Now, each of these messages needs to be processed by the CPU on the remote machine. And with the fast RDMA networking, the CPU usage is actually the bottleneck. So the differences in performance in that graph I showed you before between TCP and RDMA are down to the CPU overheads. Right? And so this is a fair amount of CPU overhead. Right? Pretty much all the participants have to do some CPU work. So in FARM, we redesigned this to reduce that CPU bottleneck. Right? So the FARM commit looks completely different. We have a lock phase where we send a message only to the primary copies and only to the primary copies of objects that we want to modify. So read-only participants don't have to do any work. Right? We then need to have an additional validate phase because we actually did less than the prepare phase of a two-phase commit. Right? And during the validate phase, we check all the objects that we read but didn't write to see if they've changed. And this involves a one-sided RDMA read of the object header, which includes a version timestamp. If the locking and the validation succeed, we can commit the transaction. And what we do is we first write a commit entry with all the data to all the backups. Right? You'll notice the backups haven't been participating so far, but we do need to make sure we commit at the backups for fault tolerance. This is a one-sided RDMA write. So that dotted line says we only need to wait for the remote NIC to acknowledge our write. We don't need to wait for the remote CPU to acknowledge it. And then finally, we can commit to the primaries and expose our write to other transactions. And so if you look at this, we need to do a bit of CPU work there, but on far fewer participants than with two-phase commit. And we need to do some CPU work over there in order to expose the write, but it's off the critical path of this transaction. And backups eventually do need to take this replication log and truncate it. And so they need to do a bit of work, but this can be lazy and batched. Right? So overall, we've reduced CPU a lot at the cost of adding some network round trips. But for the hardware we're looking at, this is a good trade-off because those network round trips are one-sided RDMAs. So the ACK comes straight back from the remote NIC. Right? So we don't pay the latency costs of waiting for the remote CPU to get dispatched and do some work. So as a result of this and several other optimizations, Farm has really good performance. Right? So we have high throughput. So this is the standard TPCC database benchmark. The x-axis is the usual figure of merit for TPCC, which is TPMC, but now in millions. And the y-axis is latency in milliseconds. And this is running on 57 machines. And I think the interesting thing is not only can we have very high throughput, we can have close to peak throughput with a 99th percentile latency under a millisecond. Right? So we don't have to trade throughput for latency as many TCP-based systems do. Today, many scale-out systems that need to meet a latency SLA run at very low utilization, 60%, 50%. And that's so that they don't violate their 99% SLA. But if you run at 50% utilization, in a sense, you're buying twice as many servers as you need to, right? So we thought it was quite important to have good latency even at high utilization. Scalability is also good, at least when you're running on a single switch, which is this testbed result here. So this shows the number of servers going up to 90, which is the size of our cluster, and close to linear scalability in throughput. And something that is really important for online services is high availability. So here I'm showing you the throughput of our 57 machine test cluster on the y-axis and time progressing in milliseconds on the x-axis. And where that red line is, we killed 2 of the machines, right? And this caused Farm to initiate failure detection and automatic recovery. And within 67 milliseconds, we were back at full throughput. And to put this in context, 67 milliseconds is less than the tail latency of some other systems, even when they don't have failure, right? So arguably, we could hide failure under tail latency and make it completely invisible to applications if we could do this consistently. So to give you an idea of sort of history of Farm, if you like, how long does it take to do a project like this? I think we had the early ideas in about 2012. That is when Alexander Dragojevich's PhD started, and he was the guy who came up with some of the original ideas for Farm. And so a small number of us spent some time working on the design, building a research prototype, publishing a couple of papers, and then towards the end of that sort of 2.5, 3 year period, we thought we had enough evidence to present to the company leadership about the potential for Farm. Right? And so they said, fine. We got resources to push Farm to production, as well as to expose it to some internal customers via a graph database. So we put a substantial engineering effort both into designing and building this graph database on top of Farm, as well as making all the code production ready. Interestingly, something I'm not going to talk about in detail now, but feel free to ask me if you're interested. During the course of this, we found we actually had to do some extra research, if you like, which we didn't expect, to fix an issue that developers were seeing, right? And this was that the first version of Farm did not have this property called opacity. And it was our experience with developers that convinced us that this was actually more important than we'd realized. And so we changed Farm to have opacity, and this is something we've submitted a paper on just now. in this last summer, we went live, so that was very exciting for some internal customers, and hopefully more internal and maybe one day external customers as well. But that's all in the future. Right? So that's sort of a brief history of one of our 5-6 year projects. Let me switch to talking about something we started much more recently, a project in its early stages, and which was actually based on some of the things we learned from Farm and started by the same guy, Alexander, who he and I started Farm. Right? And while I was talking from Farm, you might have already seen this issue pop up, that NICs were getting so fast that CPUs became the bottleneck. Right? It turns out that's also true for storage, at least for SSD flash storage. Right? So both for SSD flash storage and modern NICs, I/O bandwidths are on this fantastic curve. Right? And CPUs are not keeping up, at least general purpose CPUs. Right? Effectively, Moore's law has ended, and this exponential growth has stopped. It's been almost flat in the last few years. Right? And that means increasingly CPUs are becoming the bottleneck because these other components are still on that Moore's law. So something that you're all probably aware of is that one of the consequences is people are pushing compute-intensive workloads to specialized hardware. Right? They're offloading. So within Microsoft, for example, we have this very widely deployed system called Catapult, right, which also came out of research from some of my colleagues in Redmond. And this basically combines the NIC with an FPGA in order to offload a lot of CPU-intensive computation. Right? For example, machine learning. Right? But also infrastructure acceleration, which is really important because we're also a public cloud provider, or we're very much a public cloud provider providing infrastructure as a service. So there are actually expensive operations on the data path, like network virtualization, that they got big benefits from offloading some of that to the FPGA. And in some cases, application-specific tasks or modules also get a big win from being offloaded to FPGA. But what we noticed is that while this is great, we still, in this architecture, have these expensive and power-hungry components, right? We still have these CPUs, and we're paying for them. We're paying the dollars, and we're paying the watts. And DRAM as well. And moreover, in this architecture, that very high throughput computation that runs on the FPGA has a relatively small amount of DRAM attached directly to it, and if it wants to access the much larger amount of host attached storage, it still has to go through the CPU. So we thought, why don't we cut out the middleman, right? Can we build a system where we can put enough on the FPGA and attach storage directly to it such that this can form an effective unit for some applications at least, right? And this storage really could be DRAM, it could be flash, in the future it might be NVRAM such as 3D Crosspoint, depending on the sort of cost per gigabyte, power, and performance trade-offs that you want to achieve. Right? But the key point is CPU-free computation. Right? And in the cloud world, it makes a lot of sense not to design this sort of node by node, but think about how an entire rack of this stuff would look. Right? Because that's really how we deploy stuff in data centers. It's really the minimum unit of design that we should be thinking about. And so what we envision is a rack full of FPGAs and different kinds of storage that, as a whole, provides huge amounts of throughput at low latency, low cost, and low power compared to CPU-based solutions. It's early days yet, right? So there's a lot of questions we haven't answered. So what exactly the right system design is going to be at the rack level? What's the programming abstraction for applications? You know, eventually our FPGA is going to be the right answer, or will we have to move to a specialized ASIC for some of these applications? We don't know, right? Early days. Okay. So I'm going to pause for a moment, because I'm going to switch tacks now. and talk about storage, right? Just as important, if not more so, for Azure as computation, right? And specifically, I'm going to talk about what we're doing in the cold storage area. And the motivation for this is very simple, right? As a species, we literally are generating exabytes of data per year now, right? And we would like to store all this data. And as Microsoft, of course, we would like to store a lot of it in our cloud. But the problem is that the storage is too expensive, right? And this gap is widening, right? Now, much of the storage is likely to be cold, so it's not going to be accessed frequently. So the idea is, if we can substantially reduce the cost per gigabyte of cold storage, then we could store a lot more, right? And at the kind of scales I'm talking about, the question really is, how would you store a zettabyte of data at reasonable cost, right? When I said exabyte earlier, I was wrong. We actually generate about a zettabyte per year. That's 10 to the 21, right? And so if we can substantially reduce the cost per gigabyte at this scale, right, then we can move that line up. So if you look at existing storage technologies, right, and you put them on an axis of access frequency versus the latency they provide, right, for hot and warm data, right, we have technologies that provide good access latency, but the cost per gigabyte is really high. For cold data, we have tape. One of the problems with tape is that when you do want to access your data, it can take minutes to hours, right? There's a huge amount of mechanical movement involved over fairly large distances, right? So if we rephrase that earlier question and say, how would we store a zettabyte of data at reasonable cost and a reasonable access latency, right? If we can fill this gap here, then we think we would be able to do that, right? Something that's significantly cheaper per gigabyte than hard disk drives, but has much lower access times than tape. Think seconds rather than minutes or hours. And so Pelican was our first project addressed at this space, right? And Pelican is a rack-scale storage design, right? And based around spun-down archival-grade disks. So archival disks are essentially disks that have been optimized for the manufacturers for high capacity and density and low cost per gigabyte rather than for performance, right? And one aspect of cost at the data center level is also the amount of floor space that your storage solution requires, right? Because there's only so many racks you can fit in a certain amount of floor space. So Pelican is actually optimized to pack an insane number of disks into a given amount of floor space. So this particular design, for example, has over 1,000 hard disks, right, in a standard rack. Now, this density comes with some interesting properties. One is that we had to use vertical cooling, right? So we have columns, vertical columns, and that's where the air flows. It turns out that with this density and with this vertical cooling, we can only afford to have one disk on per vertical column at a time, right? We also have power constraints. So each of these horizontal trays, which has 6 to 8 disks, can only have 2 disks active at a time within the power budget, right? So overall, that means we have a design where roughly 8% of our disks, at most, can be active at a given time, right? And to achieve ultra-low costs, we actually exploited this fact. So it's something we call right-sizing. So for example, all these disks are connected to just 2 low-power servers, so we save a lot of money on CPUs and servers. We have 2 and not 1 for fault tolerance. They're attached via a PCI bus that's stretched using commodity components over all the 1,000 plus disks. And to save cost, we made sure that we provided exactly as much PCI bandwidth and exactly as much off-rack network bandwidth as was needed for those 8% of disks, because there was no point in spending money on any more bandwidth, right? We also had to solve some interesting design challenges, which is most of our disks spend most of their time being spun down, and we have to spin them up every time we switch the set of disks that are active at any given time. So we had to investigate what the implications were for failure and latency. And because we have this disaggregated design, right, where we need all the data to be able to fail over between two different servers, we had to come up with a way for disks to migrate between servers on that stretched PCI bus. So when we'd done all that, what we'd done is basically we'd eliminated almost all the cost except the hard disk. Right? So hard disks were now the limiting factor to a large extent for both density and cost. Right? Now, this would have been great pre-2005, because pre-2005, hard disks were on an exponential Moore's law of improving areal density. Right? Unfortunately, after 2005, they've had to rely on less Moore's law type techniques. Right? For example, adding more platters by packing them more densely. Right? And these techniques don't necessarily scale indefinitely in the same way, and they become increasingly challenging. So for example, once you get the heads too close to the platters, you have to fill the whole disk with helium, right? Otherwise, you run the risk of damaging your platters. They've also come up with shingling in order to further improve the effective density of your hard disk, right? You reduce the space between tracks. We think that these techniques are hitting a wall or will hit a wall very soon. And so one thing, for example, that hard disk vendors are relying on for future improvements in capacity is energy-assisted recording, the so-called hammer and mammer, right? Now, these apparently are very challenging because we've been hearing them about them for 10 years now, and they're still not commercially shipped. And even with those, it seems likely that around 2025, right, disk capacity is going to flatline. So no more Moore's law. Right. There's also another challenge with hard disks, right, which is they fail every 3 to 5 years. Right? In fact, if we step back a little bit and look at the storage technologies over sort of the evolution of human history, we've done very well on density, right? Really well on speed. But in terms of longevity, actually, in a sense, we've gone backwards compared to these stone and clay tablets that can last for millennia, right? And lifetime is particularly important for this cold data that we're targeting, right? You might need to keep the data for a fairly long time before someone wants to access it. Right? And a device with a low lifetime means you have to spend increasing amounts of cost. As the capacity goes up, you have to spend increasing amounts of time and cost and effort in repeatedly migrating the data, checking for errors, and writing it to new devices until those fail. And a lot of this, we thought, was because these storage devices, these legacy storage devices, were not really designed with the cloud in mind, right? In the cloud, there's no particular reason we need to address all the engineering challenges that go into building one of these 3.5 inches with 14 terabytes in it, right? We can choose any form factor, at least up to rack scale, right? We can choose any media if we want to, right? We're really not constrained as long as we can deliver the cost point we need to deliver. And so we thought, right, what if we rethink from the ground up what cloud cold storage should look like? And so that's what Project Silica is about. Right? We're designing it from the media up. The media in this case is just glass, so that has nice properties in terms of it's very cheap and it's very durable. So the cost per gigabyte and the longevity should be really good. Right? In Silica, we etch the data into the glass, into the interior of the glass, so it's protected from surface effects using lasers. Right? So at least in theory, these pieces of glass and the data in them could last millions of years, also have some nice properties for the data center environments, such as they're not affected by electromagnetic fields. Obviously, there are things that can cause you to lose the data, like breaking the glass, but we think that in a data center environment, we should be able to protect against those kinds of issues to a large extent. right? So to write to a piece of silica glass, we use an ultra-short femtosecond pulsed laser with a beam that is tightly focused onto a specific layer in the glass. And there is a non-linear optical process. My optical colleagues assure me this is the right terminology, which modifies the material to create our basic unit of storage, which is a voxel. Right? And this is a truly three-dimensional technology, right? So this is not like the surface of a hard disk or even an optical disk, which is essentially a surface technology, right? So one of our blocks of glass basically looks like this with many tracks. We're using some legacy terminology here. Imagine each track going inwards into the screen, right? And each track is a stack of layers, and each layer is a 2D array of voxels. So once we've written the data, we need to read it back. The way we do that is we focus a camera on a specific layer and a specific track, right? We take multiple images, and we combine those images to compute an entire 2D array of retardance and orientation from which we can recover the original data encoded in the voxel, right? The way we change the data we write is by changing the beam polarization of the laser. So one thing we already found is that to achieve high density, you want to go to many, many layers. But as you increase the number of layers, these images get noisier, right? And it becomes harder to decode the data with high accuracy. And this is something we're still working on, but something interesting we've already found is that machine learning approaches actually seem to improve the decode accuracy significantly over traditional approaches. So that's a promising area that we're pushing on. So this was sort of a high-level summary of Project Silica, right? And it's really a very ambitious project, and we're nowhere near the end yet, right? We're trying to design cloud storage really from the media up. And I want to reinforce something I said earlier, that we really couldn't have done this if we weren't truly interdisciplinary, right? We have physicists, optics experts, signal processing people, systems people such as myself, and machine learning experts all pulling together because we have the same goal. Right. Let me switch to talking about another thing we're doing in optics, right? Which is optical networking, perhaps less esoteric to this audience, right? And I'm going to talk about one of our optical networking projects, which is aimed at the network inside the data center, the NDC network. So if we look at how we interconnect within a data center today, we have racks of servers, and they're interconnected by some sort of topology, factory, cross network of electrical packet switches, right? And this is a design that we've been using unchanged for over a decade. Now, because electrical cables don't have the reach we need for the size of a data center, all the cables between these switches are already optical. And what we're doing at each port is converting the optical signal to an electronic one, right? Doing the packet switching through a very high performance ASIC, and then converting it back to optical for the next hop. Right? So demand for this bandwidth inside the data center is going up exponentially because this is being driven by these increasingly powerful hardware accelerators as well as the faster NICs at the edge, at the rack level. So far, we have been able to provide this bandwidth at a high but, let's say, acceptable cost because the switches also have been on a Moore's law trajectory. So the number of gigabits per second per dollar that we can get has also been going up. We think this is going to hit the CMOS scaling limit relatively soon, in the next 5 to 10 years, right? And the reason we're investigating optical networking is to see if it can take us beyond this limit, right? So Project Sirius is a project to design an entirely optical core network for the data center above the rack level, right? And the design uses entirely passive optical components in the core. So we don't have those transceivers, which are surprisingly expensive, that do the optoelectronic conversions. In fact, we have no CMOS components, right? And what that means is not only can we sidestep, hopefully, the CMOS scaling limit, but also lower latency, because we don't have to do this looking up the packet header on each hop and then switching it through the ASIC. So if we pull this off, we will have more bandwidth per dollar and per watt with lower and more predictable latency, and we'll be able to get bandwidth beyond that CMOS scaling limit. It's not as easy as I made it sound, right? There are some huge challenges. One of them, for example, is that optical switching is essentially circuit switching. And we're trying to provide a packet-switched abstraction at the rack level. And for the kind of bandwidths we get today for top-of-rack switches and the smallest packet sizes that applications can use, this actually involves switching at nanosecond timescales, and that is something we've been working on. All right, so let's step back a little bit. And I made this slide because I wanted to sort of think about, well, why is cloud important, right? How has it influenced our research? It turns out it has influenced us a lot. So about 10 years ago, right, we were doing research, for example, in storage, but this was driven mainly by what we call enterprise workloads, right? Things that our customers might run on-prem. At around the same time, we were doing some of the early work on a rack-scale networking architecture. So we were already thinking ahead to where we could design our own racks for our cloud data centers. And then we brought those two together in a sense, or at least we brought the lessons from those two together to do the Pelican project, which was the rack full of disks that I showed you earlier. About 5 years ago, 6 years ago now, we started working on Farm, and Farm was already very much in the cloud world. We knew that eventually where we wanted to deploy it was in our data centers as a service. And then more recently, I told you a little bit about Honeycomb, which was the FPGA-based CPU-free computing. That's really, you can think of it as taking this rack-scale design, combining it with some of the things we learned from Farm, and then adding this radical new idea, which is getting rid of CPUs. And also around 5 years ago, 6 years ago, we started investing in optics. And the original goal was to build this data center optical network. But actually, we found that once we built up a critical mass of optical expertise, these are researchers, they're very smart people, and they're looking for things to do. So they started coming up with ideas. So for example, why not improve the inter-DC network, right? Involves a different set of techniques, but largely overlapping sets of skills and expertise, which we already had. And of course, once we had enough confidence that we knew what we were doing in optics, and we had all the storage expertise, and together we were able to go for something very radical, which is Project Silica. Right? And so if you look at that, most of this picture and all of it since 5 years ago is basically driven by the cloud, right? It's really what provides us at the moment, and probably for the next decade, most of the motivation for the big research challenges that we're trying to solve. Okay. So okay, I think we have some time, right? I'm going to talk a little bit more about security, and then we'll leave time for sort of Q&A. So security is hugely important for the cloud. I don't think I need to convince anyone of that. So we have this initiative, which is a collaboration between Azure and Microsoft Research, which we call Azure Confidential Computing. And there's a bunch of different things they're doing, but overall you can think of the goal to be to offer an infrastructure where neither cloud administrators, so sort of insiders if you like, nor hackers can access or tamper with customer code or data. Right? You can take your on-prem stuff and run it in our cloud with as good or better security. That's what we're aiming to provide. A lot of the technical research has been on trusted execution environments, right? So, for example, SGX enclaves, right? And essentially what these are is they are containers for code and data which are isolated from all other code and provide remote attestation so that the customer knows exactly, can trust that the code they think is running in the enclave is running in the enclave. Right? And there are many implementations of these. Perhaps Intel SGX is the best known. So we have several projects around enclaves. So one is, for example, how do you build a secure database service out of enclaves? So EnclaveDB is an interesting project from some of my colleagues where they've split the architecture, right? So the compute-intensive part runs in a high-performance in-memory database engine in an enclave in the cloud. The secure, trusted, but if you like, metadata operations, for example, compiling stored procedures, managing keys, run on a trusted client that runs on premises. And everything else, the network, the cloud storage, the actual servers that host the enclave are untrusted, the part in red. Right? And so what this gives us is strong security properties while keeping the TCB, the trusted computing base, small. And a small TCB is very important because the more code you trust, the more likely it is to have bugs and exploits. Right? And at the same time, we're able to get very high performance because we've split it such that the high performance bit runs inside the trusted hardware. Okay. A few months ago, Azure also announced the Cocoa blockchain services. I'm sure all of you have heard of blockchain. This was also a collaboration with Microsoft Research. And basically what Cocoa offers is the blockchain abstraction, but implemented very differently from how traditional blockchain is done, right? It's implemented as a set of nodes with state machine replication for fault tolerance running inside enclaves. So this has quite different properties from traditional blockchain, right? One of them is higher performance, but another one is enclaves also provide confidentiality, which is very important for some potential applications and which traditional blockchain doesn't provide. And the third security project I want to talk about is a relatively recent one, which is based on this observation that enclaves are very good at protecting computations running on CPUs. Like if you have an Intel SGX, you can run Intel x86 code. But as we've already alluded to, increasingly computation, especially for machine learning, has indeed moved to GPUs and and is moving to custom machine learning processors, right? And the reason is very simple. These can provide orders of magnitude more performance for these workloads than general purpose CPUs. So it becomes important now to protect the code and data running on those devices as well, right? And that is what this project is about, right? Logically, you can think of it as extending, logically, the CPU enclave to include a GPU or other accelerated device. And that requires some hardware extensions to the hardware device, as well as a lot of system support. So you've seen this slide before, just sort of summing up. Increasingly, we find that, at least in the systems area, the cloud drives most of our research because within Microsoft, there's a huge business need, right, to stay ahead of our competitors and to keep up with our customers. And also at the scale and the level of the challenges means that there are lots of interesting systems problems to work on for researchers, right? And at a very high level, I think the biggest set of challenges coming up. So you might have noticed that our earlier projects that I talked about, Farm and Pelican, they were really about looking at the trends in hardware and squeezing as much performance out of the hardware, sometimes by redesigning at least at the rack level, right? But at the end, once we've squeezed everything we can out of the hardware, which can be orders of magnitude as in Farm, as demand grows, we are back to relying on Moore's law, right? And so the real challenge is going to come when for each of these technologies will be at different points in time, this kind of growth stops because it's unlikely that the demand will stop at that point, right? And so the real opportunity for research is how do we take it beyond there, right? Optical networks, optical storage, whatever your next big idea. So that's really it. I'll leave those up, but you can also ask me for links to more information, and I'm happy to take questions.